Howdy class. For the second problem of the review, we're going to be doing a batch distillation problem. In this problem, we're given that we have 100 moles of liquid inside of a still. The composition is 20% of a component A, 80% component B. We're given that the equilibrium data can be modeled by this quadratic, where x and y are fractions of A. And we're told we distill off 63.2 moles of our liquid at 1 atmosphere. We're asked to find the average composition of our vapor, YAV, and the composition of the remaining liquid. And so first, we're going to look back at our formula sheet and find our key equations. For finding our x2, our key equation is that the natural log of L1, our original amount, over L2, the amount of moles that will remain at the end, is equal to the integral from x2, our final composition, to x1 of dx over y minus x. We want to remember that L1 is the original moles. L2 is remaining. X1 equals original composition. And X2 equals final comp. The other equation that we'll need is our mass balance. For our mass balance, we have L1, X1. This is the total amount of species A at the beginning, is equal to L2, X2. That's the amount that will be left over after the distillation, plus L1 minus L2, the amount distilled, times the average composition of that which was distilled. Rearranging this, YAV, subtracting this over, dividing by this, gives us L1 X1 plus or minus L2 X2 over L1 minus L2 equals our average composition. And now we can go ahead and write what we know. So we have that L1 equals 100. L2 is our 100 minus the amount of moles that we distill. This gives us 36.8. Since we have both of those, we can get this natural log term. We get the natural log of L1 over L2 equals the natural log of 100 over 36.8. And that's just 1. Finally, we have X1 equals 0.2 from our original composition. So we want to go ahead and find our X2 from this integral. Because we're given our equilibrium data as a quadratic, we can go ahead and plug this in for our x and evaluate the integral. So we have 1 minus y minus x is equal to 1 over minus 3x squared plus 4x minus x, which is equal to 1 over minus 3x squared plus 3x when we plug in our data. Next, we can turn our attention to this integral. We have the integral from x2 to x1 of dx over y minus x equals the integral from x2 to x1 dx over minus 3x squared plus 3x. We can go ahead and factor out this minus 1/3 term to make our denominator look nicer. Giving us dx over x squared minus x. which we can take one step further and factor that denominator. Into x and 1 minus x. Once we have this form, we can see that we want to partial fraction expand this, so we get minus 1/3 times the integral x2 to x1 of ax plus b x minus 1 dx. From Calc 2, we should remember how to do this. We multiply by our denominators, and we get that 1 equals ax minus 1 plus bx. We can see that a minus a is going to be our only constant term, so that's equal to 1. So a equals minus 1. And then from our x terms, we have that a plus b must be 0. And so this gives us that a b is equal to 1. We can go ahead and plug that into what we had up here, giving us minus 1/3 integral from x2 to x1 of minus 1 over x plus 1 over x minus 1 dx. We should also remember from Calc 2 that the integral of 1 over x is log of the absolute value of x. X minus 1 will be the log of the absolute value of x minus 1, as it's just a chain rule. So this gives us minus 1/3 times minus ln of x plus ln x minus 1, evaluated from x2 to x1. We can use our log rules to go ahead and combine these into 1. So this gives us minus 1/3, the log of the absolute value of x minus 1 over absolute value of x, evaluated from x2 to x1. Finally, we can go ahead and plug in our endpoints. And so writing that down here to get our final equation, we're going to get minus 1/3 times ln absolute value of x1 minus 1 over absolute value of x1 minus ln absolute value x2 minus 1 over absolute value of x2. We can bring this minus sign inside and get 1/3 of ln x2 minus 1 over x2 minus ln x1 minus 1 over absolute value of x. Finally, we can use our log rules one last time to combine this into 1/3 times the natural log of x1, x2 minus 1, x2, x1 minus 1. So now that we have that equation, we can use it with our known values to solve for x2. Okay, now we can go ahead and solve this to find our value of x2. So we want to set this that we just solved for equal to 1, which we solved down here as the natural log of L1 over L2. We also need to plug in our x1 values, so we're going to do that. We get 1/3, 0.2, x2 minus 1 over absolute value of x2, 0.2 minus 1 equals 1. We're going to multiply the 3 over and then take the exponential of each side. That gets rid of our fraction, so we get 0.2. Or gets rid of our log term, so we get 0.8 absolute value of x equals e to the 3, which we're going to round to 20 for this. Finally, because we know that 0 is less than or equal to x2, less than or equal to 1, we can rewrite this to lose the natural logs. So we get 0.2, 1 minus x2 over 0.8 x2 equals 20. Once we have that, we can multiply by the denominator, collect our terms, so we get 0.2 minus 0.2 x2 equals 16 x2. This gives us 16.2 x2 equals 0.2, gives us x2 equals 0.2 over 16, which is 0.0123. Now that we have that, we can go ahead and fill in this blank. The next thing we need to do is use this equation to solve for our y average. So we can plug in all of our values now that we know them, and we get y average is equal to 100 times 0.2 minus 36.8 times 0.012 over 100 minus 36.8. And we evaluate this as 0.309. Plugging this in here. And that's everything that we needed to solve for here. So for the batch distillation, the key is being able to evaluate this integral here. You can do that numerically. You can do that on your Inspire or TI-84. You can do it by hand like we did over here. However you're able to evaluate that is good. From that, you can get your X2 and then your average vapor phase composition. And that's it for review 1. Stay tuned for exam 2. The second exam review, we'll do a multi-component distillation example.